we're going to talk about a very famous Big Al scientist named Alfred Wegener, although it starts with a W, Big Al. We say it Wegener because I believe he was German. And how his idea of continental drift became what we have today as the theory of plate tectonics.
So what was Wegener trying to do? Well, he was trying to figure out why we have land features where we have them on planet Earth. He came up with this whole hypothesis called continental drift, which is basically saying the continents are drifting around on top of the Earth. And as they move, collide, separate, etc., they create all these landform features that we see, mountain ranges and valleys and volcanoes, etc. So what were his lines of evidence? Well, here they are.
So he had four things that he was able to use to help support his theory. And we have the page numbers here. Those would be good to jot down. First was the fit of the continents. So they have Pangaea. Some of you have heard of that before, the huge continent when they were all together. There's a whole bunch of names for the different ones throughout history. And you can see that on page 77. But they actually fit together like puzzle pieces. If you look at Africa and South America, that's what they're talking about. The second one, similar fossil records on different continents. So you're going to find the same species recorded in the rock, although now there's a giant ocean between them. The third one, same rock formations on different continents. There's literally identical rocks that are separated by an ocean. They were at one time connected. And then four, evidence of similar past climates on different continents. We'll go into a little bit more detail about that one in a little bit.
All right. So detail, as you can see here, I mean, this is kind of what Earth looks like today. And if we were to go and put all the puzzle pieces together, oh my goodness, all the continents would kind of fit. And this is kind of the first thing. The continents fit like puzzle pieces, which is what Wegener said, oh, maybe they were together. And, you know, since Pangea or Pangaea, which about 225 million years ago, you can see over time how the continents have moved towards their present place, of which if we're going to hang out for a few more million years, we'd notice that change. Fossil evidence. I mean, how do we get these land-dwelling fossils to end up on two continents that are separated by big chunks of water? Well, maybe if they were together, the animals could freely roam. Or the same for this one right here, which is a tree plant, or this land animal, etc. But if the continents were all together at one time, it would be easy for plants and animals to move back and forth between continents because they would be one giant landmass. Fossil evidence. Another view of fossil evidence where they are today, and you can kind of match up and always pause this to show where different fossils are on different continents separated by huge chunks of water. Pretty crazy. He did a good job coming up with that. The rock formations. The rocks on the Appalachians in North Africa and part of England, Greenland, and Norway are all the exact same. The rock layers, as we learned in our last unit, superposition, all work great. They're the same age, the same layer on top of each other. How could they have formed at the same time in the same succession? Maybe they were forming next to each other. And then past climates. At one time, the whole area in white was under a glacier, ice, basically. And that's really weird because look at where India is today, to have ice way across the equator and way below the equator all at the same time. Crazy. So these were the main four lines of evidence that Wegener had, and he was laughed at.
Yep.
Pretty bad. People said he was a nut, you're crazy, this will never come. How can we really prove these? Well, over time, he died, by the way, in an Arctic expedition, I think, in the 1930s. But after his death, new technologies, we love technologies, came about. And kind of a new springing happened. And the theory of plate tectonics was born based on his hypothesis.
So what we have today is the theory of plate tectonics, which actually includes those four things that Wegener started out with. Without those four things, it would be doubtful that we would have the theory of plate tectonics that we have today. So scientists back in the 50s, 1950s, 1960s started to look at continental drift and started to see how a lot of these ideas were actually really good, particularly with new information that they were finding out after Wegener's death. So heat from the inner core moves outward and creates convection in the asthenosphere. That's something that we're discovering, and the asthenosphere actually moves the lithospheric plates, creating all major features. So all those questions that Wegener had, he was really just missing the piece of the puzzle of knowing that the asthenosphere is a plastic, fluid-like rock material that actually has the ability to flow. If he had had that and knew that, people probably wouldn't have thought he was so crazy.
So plate tectonics really tells us that the mechanism for plates movement, or the top of the Earth moving around, is due to the inner core's heat moving outwards, creating convection and moving all the plates around.
You actually have heat moving material. That's just amazing.
That's heat is the key.
Heat is moving the continents.
And the evidence, well, you take Wegener's first 4 ideas, which are still evidence, and we get 4 more new ones, which we're going to go into a little bit more detail about. These are much more complicated than Wegener's ideas. And we'll start with a pretty easy one, something we're going to do in class. Basically, they've plotted locations of earthquakes, volcanoes, mountain ranges, and trenches. And when you put those into a map, they tend to be near what we see as plate boundaries today, as we'll find out by the age of the rocks, etc., that we'll learn about real shortly.
The next one is the seafloor mapping, and there's spreading locations. So we've actually been able to figure out the age of the crust through radioactive dating, and we also can figure out through magnetic sensing what the age of the crust is. We just go over it with a boat, and there's lots of different ways to do it. But you can see it in this picture here, where the red material is that newer crust, and as you get further and further away from those deep red lines, you have yellow and green and blue. That's really older crust. But if you look at where the majority of the young crust is, it's in the center of our major oceans, which is not a coincidence.
Those seafloor spreading areas, as we'll learn about. Kind of a tricky one is magnetic seafloor reversals. And basically the key is our positive North Pole has not always been positive. Sometimes the South Pole has been positively charged. About every 120,000 years, the magnetic field of Earth switches. And so sometimes we'll have a south positive pole, and currently, like now, we have a north pole that's positive. And basically, as new crust is being created or new magma is coming out of the Earth, it's going to harden. And any metal in that magma is going to orient itself with the positive pole, whether it's positive in the north or positive in the south. And then that new rock or new crust is going to get pulled apart. So here it is, let's say, 250,000 years ago. New crust is created, and it's going to be pulled apart, and that new crust now got ripped. Some of it's on the left, and some of it's on the right, and since then we had some new crust get created, and it was orientated to the south positive pole, and that got pulled apart, and now we have the north positive pole metal orientating rocks, and that's going to get pulled apart, and we end up with this magnetic seafloor reversal where it's positive to the north, positive to the south, positive to the north, positive to the south, positive to the north. And then we go to the other side of the spreading zone, and it would be the exact same positive trend going on. Kind of confusing, but magnetic seafloor reversals. And here's a closer up view of that magma coming out, hardening right here, and then it's going to get pulled apart very slowly over time, and you get a reversal. North positive, south positive, north positive, south positive, north positive, south positive. Well, hopefully, no pun intended, you get the picture.
That picture's right from your book, and some people have a hard time understanding the instructions for that drawing, so we will make sure to go over this part in class as well. And then the 8th thing that we have is radiometrically dated seafloor drill samples. That sounds like a lot. But like what we learned about in our last unit with radioactive dating or radiometric dating, you know, you got carbon-14, which wouldn't be great for this. But you have all those other elements and lead and uranium and yada, yada, yada. We can drill down into the earth, into the rock, and into the ice, and we can figure out the age of things chemically, and we can actually line up all those core samples. And as you approach an ocean ridge, they get younger and younger and younger. And as you go over that ocean ridge, the pattern would be in reverse, and things would get older and older and older as you get away from the ridge.
So we have been able to compile all these data to create a age of the surface of the Earth in terms of how old the rocks are. And if you notice, this very light pink and yellow happens to be the last 2.6 million year color. And wherever that light pink and yellow is, happens to be where we can actually go and witness the Earth's crust or plates moving apart from each other. And as you get further away from those spreading centers, the rocks get older and older and older, as you can see color-wise, etc. It's just an amazing thing that's been created since Wegener's been dead due to new technology, but to help take his ideas and make them basically a real theory. What we'd like you to do is create it and do this Venn diagram for class tomorrow. You know, on one area, put everything that's just about continental drift right here. Put everything that's just about plate tectonics here. And if there's ideas, etc., about both CD and PT, put them right in the middle. And bring it to class tomorrow so we can share. For a little review, we're going to hit a couple quick slides. Make sure you have the evidence for plate tectonics, which are all 8 of these, including the 4 evidences for continental drift, and make sure you know what the theory of plate tectonics, what the hypothesis of continental drift and
was
how it
trying to
answer,
solve the problem
and
of
who is
why
the
we have
main
features
creator
when we
of
have
that.
features.
And the main
I mean,
reason
it's
is
not
the
that
H
bad.
word.
Big Al.
And make sure you know what the hypothesis of continental drift was trying to answer, and who is the main creator of that. I mean, that's not that bad. You can always review this. Make learning fun. Bye.
Big Al. Big Al. Big Al.